This right here is what we call the Dirichlet integral. And it looks pretty funky, right? This right here is a non-elementary integral, and it's not just that, it's improper as well, since the bounds approach negative infinity and infinity. So how do we solve this? Well, we can't just go ahead and integrate it normally. So instead, we're going to be using, well, before I get to that, actually, why don't we rewrite this really quickly? And how can we do that? Well, on the inside here, notice that you have an odd function, sine, divided by another odd function, x. Odd divided by odd, in terms of functions at least, gives you an even function. So inside of here, it's actually even. And notice how these bounds are symmetrical. Well, if it's symmetrical, then what we can actually do is just rewrite this as 2 times the integral. However, instead of starting at the negative top bound, you would start at just 0, and then the top bound would stay the same. Okay, so this is easier to think about, since you're no longer stretching in both directions. Well, is it easier to think about? Because what are you doing here, right? Okay, well, if you've seen this before, you would know that typically people like to solve this with maybe Laplace transforms. If you solved it with the Laplace transform, then you would take advantage of the property. You would take advantage of the property that is given by the Laplace transform of f of t over t, right? But how would you derive this property? Well, we would use the Leibniz rule for integration. So instead of doing the Laplace transform, right, a more complete way of starting this from beginning to end is just using Leibniz rule for integration. All right, so we have to introduce a parameter. All right, so let's call a new function I of t. So t would be our new parameter. Let this be equal to, well, we're still going to have this, right? But where would we put the parameter? Well, first thing that might come to mind is maybe inside of the argument of the sine. If you had sine of tx, then what would happen is if you differentiated sine of tx with respect to t, you would get x cosine of tx, right? And then the x on the outside of the cosine is going to cancel with this, and that would make it much easier since it's easy to integrate cosine of tx with respect to x. However, that's not going to work because notice your bounds are from 0 to infinity. You can evaluate the antiderivative of cosine at 0, but you can't evaluate it at infinity. The limit of cosine, the limit of the antiderivative of cosine, which is sine, as x approaches infinity, it doesn't exist. It doesn't exist for any trig function. So, well, now what do we do? Okay, well, instead, let's just multiply on another function that once we take the derivative of it, can cancel with this x. Since this x is bothering us, we can deal with sine, just not this x. One of the most basic functions to work with in differential calculus, integral calculus is the exponential function, right? So we can maybe introduce one of those and have it cancel with the x once we differentiate. And here's what I mean by that. Well, we can have an e to the something, right? Our parameter is t, so let's multiply t on top. And then, well, differentiating this just gives us e to the t. We want something to cancel with the x. So if we just multiply an x on top, differentiating with respect to t, x is just a constant, it gets multiplied down to the side, right? Then it cancels with the x. So this might work. But one issue with this is that, well, on this interval, does it converge? It doesn't, right? E to the tx grows really fast, really fast. So it's never going to converge on this interval. Even if sine x over x approaches 0, this right here will not converge. So how do we do it? Well, from 0 to infinity, notice that our function, the e to the tx, looks something like this, right? It grows if we go from 0 to infinity. Let's just flip it across the y-axis, reflect it, yeah? And to do that, we just make the exponent negative. So that way, because we know that this area down here is finite, right? This area diverges. So if we just flip it, then we get from 0 to infinity, it converges now. Alright, so one thing I'd like to mention before we actually do any of the math is, well, this right here is precisely the definition of a Laplace transform, right? Just replace your x with t and then your t with an s. You notice that it looks just like a Laplace transform. And that's where the idea comes from, right? But I'm going to continue doing it this way. So what's the second step to using Leibniz rule for integration? Just differentiate both sides with respect to your new parameter, right? T. Actually, before we do that, there's one more thing we need to establish. What value of t do we have to plug in for it to be equal to this guy? Well, here if we plug in a 1, it's going to be e to the negative x, so that won't work. If we plug in a 0, though, this exponential, it just goes to 1. So all you're left with is this, and then the integral, and then the 2, which is equal to this, is equal to that. So this right here is really just equal to this function when t is equal to 0. So our original integral that we're looking for the value of is just equal to I when t is equal to 0. All right. Okay, so now let's differentiate both sides and see what we get. So differentiating both sides, differentiating left side, you get di of t. Don't forget we're doing this with respect to t. And on the right-hand side, you can differentiate the whole thing, but the Leibniz rule of integration, why this matters to us, is we can swap the order of the limits, right? You don't need to differentiate with respect to... you don't need to differentiate after integrating. You can take that to the inside. It becomes a partial derivative, not a total derivative, because the way I would explain it is you're in the presence of another variable that's independent of t, and that's important to note. It's independent, right? So x is a constant in the t world. So basically, all that means is instead of a total derivative on the outside, you can drag that to the inside, and then just take the partial, right? Now on the inside right here, this is just a constant with respect to t, so I'm going to keep that right here. All we're really doing is differentiating, taking partial derivative of this with respect to t. So, partial t, yeah? And we have e to the negative tx. This is what we are differentiating. And then the dx on the outside stays the same. So, differentiating this, pretty simple, arguably. The integral stays the same. Sine x over x stays the same. These are all on the outside of the partial derivative. Differentiating e to the negative tx with respect to t, x is a constant, negative is also a constant, then this will repeat, but then by chain rule, you have to multiply negative x on the outside. So it looks like this. So the negative x gets multiplied. And then in here, you have your e to the negative tx, which repeats because of it's the exponential function. All right, and then here we get our intended effect of the x canceling out with the x, like that. Let's put the 2 on the inside and then drag the negative in front of the 2. Well, I want to keep everything inside of the integral because, well, if we have a sign and then we have an exponential, what are we going to do? We're going to do integration by parts with respect to x, yeah? So let's drag everything to the inside first, just to make it not confusing. So this integral stays on the outside now. Drag the 2 inside, drag the negative, and then let's write down the exponential guy first. So e to the negative tx, and then we can put down the sine x, and then the dx, like such. Now what we can do is just use integration by parts. Okay, and so to do this, let's just use the di method, right? It makes it quick, makes it easy. So we want to differentiate a factor. In this case, let's differentiate just e to the negative tx. Differentiating that, and remember, we're trying to evaluate this integral now, right? So the t is really just a constant. We can treat it as a constant for now. We're working with respect to x. We're trying to get rid of that integral. So what we got to do is, differentiating this guy with respect to x, right? Negative t is a constant, so we can drag that out to the side. for the first derivative, and, well, let's do 2 iterations, right? Let's differentiate this again. Negative t is just a constant, just ignore that for now. And then we just got to differentiate this thing again, drag the negative t to the outside. Negative t times negative t is just t squared, e to the negative tx. All right, now let's do a couple iterations of integration. What we have left is the negative 2 and the sign. All right, so 2 is just a constant. We can look at the function as negative sine x. Integrating negative sine x, you get positive cosine x. So the negative and the sine become a cosine after integrating 1 iteration. And then integrating this again, the 2 still stays, and then the cosine becomes a sine. All right, now, per the rules for the DI method, we want to multiply diagonals and then integrate the row. And don't forget, now we have bounds, so we got to plug those in as well. Let's just go ahead and do it all. So we got this times that, so let's put down 2 cosine x. Well, you know what? Typically you would put down the constant first, then the exponential, and then your trig function. So it would look like this. Negative makes a positive, so you're adding. Let's put down the 2, and then the t, and then the e to the negative tx, and then finally your trig function. All right, and then the last row we have to integrate. And now this looks pretty bad. In fact, it looks equivalently as bad as the original, but that's the point. It's equivalently as bad as the original. It's the same, almost the same integral at least. So right here, this is just addition. And then we have an integral from 0 to infinity, right? It's the same bounds, and it's just, you're integrating this row. The 2 right here, this can stay on the inside. And in fact, I want to introduce a double negative, since I want this integral to look the exact same as this integral, because this is a repeating case. And I'll explain that in a second. Maybe. It probably shouldn't be necessary. So let's introduce a double negative. Well, if we want a negative on the inside, like we have here, then we also need to multiply a negative on the outside. Negative makes a positive. This 2, we're going to keep it on the inside, kind of like we have it here. E to the negative tx and sine x, we're also going to keep on the inside. And then here, next, we got the t squared, but notice that this integral is with respect to x. Yeah? This t squared is just a constant. Let's bring that outside. So it would look like this. So we got negative t squared and then this integral again, which is what you had here. All right? So this is equal to this. And one more thing for this line right here. You had integration bounds, so we also gotta plug those in. So this is from 0 to infinity. Okay, well, how do you evaluate this, right? First of all, I want to get that done with. So let's go ahead and focus on this part first. Well, you can factor out the 2 times e to the negative tx, right? So let's do that first. And then for this one, you're just left with cosine. And then for this one, you're left with the plus t sine. Don't forget, we're going from 0 to infinity. And in fact, right here, you can already see the answer. This part in here always remains bounded, right? No matter what value of x that you set, as long as it's finite, then it's going to be in between, it's going to be bounded, basically. These are trig functions. They're constantly oscillating. They never, go anywhere, right? However, this, on the other hand, approaches 0. So, if you plug in infinity, that is, right? E to the negative infinity approaches 0. 0 times anything finite, right? This is always finite, is going to just be 0. So this top infinity right here is actually just going to evaluate to 0. All right, so this right here is equal to 0 minus, plug in the other bound. Cosine 0 is just 1, right? So there's a 1 plus. Sine 0 is 0. Anything times 0 is 0. So there's just this 1, right? And then 1 times anything is just that thing itself. So all we're really doing is plugging 0 into here. A 0 in the exponent, anything times 0 is 0, e to the 0 is just 1. So, and 2 times 1 is just 2. So, in actuality, this whole thing, well, evaluates to this, which evaluates to this, right? So that's this whole part right here. Okay, so that's that. Let's move this up here. So we saw that this is equal to this whole thing, and these two terms, evaluated from 0 to infinity, just gives you negative 2. So, we can put down the negative 2, and then we still have all of this crap, which I'll just really quickly put down. Alright, and from here, I'm going to get rid of this work, right? You could have done it more rigorously with probably squeeze theorem for this part and the infinity. The 0 is just plug and play and you're good. This right here, you have one of these integrals on the left side and negative t squared of them on the right side. If you add t squared of them on both sides, then on the left side, you're left with 1 plus t squared of them. On the right side, well, negative t squared plus t squared just gives you 0. So let's just add this whole thing on both sides, right? So that way all the integrals are isolated on one side. Okay, so this implies adding t squared of these guys on both sides, right? 1 plus t squared is just 1 plus t squared. So on the left-hand side now, we have 1 plus t squared of these integrals. From 0 to infinity, negative 2 e to the negative tx sine x dx. On the right-hand side, adding t squared of them, it's going to cancel out with this negative t squared of them. All you're left with is the negative 2, right? Pretty cool. And I should put this plus t squared in red, because this is a modification we're making. And then finally, well, what are we trying to do? Let's isolate the integral by itself, right? Since that's the whole point, we're trying to get rid of the integral. And to do that, we just got to divide both sides by 1 plus t squared. So, what do you get? Integral from 0 to infinity, negative 2 e to the negative tx sine of x dx. This is equal to, well, you have this negative 2, and you now want to divide it by whatever's going on here. 1 plus t squared. So there you go. This, we got this by itself again, right? It's equal to this, right? So therefore this is also equal to that. Is equal to this, is equal to that, is equal to this, right? So basically all this is trying to do is we simplified this whole thing into that right there. That means the first derivative of I with respect to t is just that. And, alright, so now what? Now what do we do? Well, I'm gonna really quickly, like this. Alright, so now what do? Well, remember what our objective was. It's to find I of t at t is equal to 0. So we have to find a way to go backwards from I prime to just I. And how do we do that? We integrate, right? So let's integrate both sides with respect to t. And this right here, the I prime of t, you can actually write it as, well, di of t dt, right? Kind of like I wrote it over here. So let's go ahead and integrate both sides of this equation to get back to our original I of t. And this is an equivalent form, right? Because we see that this is equivalent to that. That means if we integrate it and then we find the constant that comes with it, well, that means we found an equivalent form for just I of t by itself. We found that this whole thing right here is equal to, well, something else that we're going to look for right now. And how are we going to do that? Just integrate. So integrating both sides. Integrating the left-hand side with respect to t, you get negative 2 is just a constant. And then 1 over 1 plus t squared, obviously inverse tangent of t. Okay. And then, well, don't forget you have to add c, right? Because this is just an indefinite integral. All right, on the right-hand side integrating, you just get simply I of t by itself, right? If you, well, yeah, the integral of a derivative is just the original function by itself plus a constant. Alright, so what is this constant? Well, let's just plug in some values to try to find out what this constant is. If we can figure out what the left-hand side is, like if we can plug in a value of t to figure out what the left-hand side is and the right-hand side, then we can find c. We can just isolate c, yeah? Alright, the right-hand side. How do we find, what value of t can we use? Well, what is I of t, first of all, right? I of t, sure, you can say it's this thing, but that's not really helpful to us. We're looking for c, so we need something that can give us a dead value, just a number. Alright, so, well, only other place where we can find I of t is up here, right? Where we originally defined it. So, we have to plug in a value for t that can hopefully just give us a nice value to work with. So, what value of t can we plug in? Well, 0. If you plug in 0, well, that's not going to work, since we saw that it's equal to this guy. And we don't know what that's equal to, right? So what else? Well, typically a good idea is to try to zero out the integrand. If you can make it 0, then you know that I of t at that value that makes it 0 is just 0. So this becomes 0. And then you can plug in the same value of t here and then solve for c. So how do we do that with this exponential right here? Well, e to the negative infinity approaches 0, yeah? That's obviously true. So what if we just plugged in infinity for t, right? If we plug in infinity times anything is infinity. E to the negative infinity approaches 0, and integrating 0 gives you simply 0. So at t approaches negative infinity, right? So let's just plug that into here and here to find a value for this, a value for that, which we can plug in here since this is I of t. So why don't we do that on the left side of the board? So I of t approaches positive infinity. On the right hand side, well, earlier we determined that this exponential goes to 0. Anything times 0 is 0. Integrating 0 gives you 0. So this is equal to this. Alright, well, notice that I of t is also this thing. So plugging in t approaches infinity, we also have to do that here. So what's inverse tangent of infinity? Inverse tangent, it approaches pi over 2 as t gets bigger and bigger. And then 2 times pi over 2 just gives you pi. And then you still have the negative. So all in all, if you plugged in t approaches infinity into here, this right here evaluates to negative pi. But don't forget you still have the plus c. And this is the point, right? If you can get rid of the variable, right, by finding values that you can just plug in there and there that are true, you can just go ahead and isolate c. Add pi on both sides, well, you get that pi is equal to c. So, therefore, you can just plug in pi there. So let's rewrite this. This is negative 2 times the inverse tangent of t plus c is equal to just pi. And this is still equal to I of t. Alright, what's the only thing left? Notice that, well, what's the original goal? The original goal was to find this, yeah? And to find this is just equal to I of t, where t is equal to 0. So now, the only thing stopping us is we gotta plug in a 0 into our function I. So why don't we just do that? Let's plug in a 0. I of t equals 0. First of all, we know that this is equal to that, so I'm going to write it down again for the sake of closure. We get sine x over x dx. Alright, but we also know that the I of t is not just equal to this, it's also equal to this, right here. So we have to plug in a 0 into t here. Inverse tangent of 0 is just 0, and negative 2 times 0 is 0. What are you left with? This goes to hell, right? All you're left with is this pi right here. So I of 0 is just pi. Pretty cool, pretty cool. And now we've just proven that this right here is true. The Dirichlet integral evaluates to pi. Nice. And now I want to go ahead and cube the entire integrand and see if we can pull off something similar. Well, this is fun, I guess. So, what was it? Integral from negative infinity to infinity of sine cubed x over x cubed dx. Now, as I mentioned earlier, we're going to be using Leibniz rule of integration for integration. But here, we can just go ahead and let the argument of the sine have a parameter inside of it. All right, since this time it actually might work. Because like once you differentiate it, right, the x is going to come on the outside, and you're not gonna have to plug in bounds immediately, so it might actually work, and you don't need to introduce the e to the negative graph, right? So you would let a function, I'm still gonna write this as I of t, let I of t equal to, well, this thing, however, just parametrized with the t inside of it. Sine cubed, and then instead of x, you get t x, and then the bottom is just x cubed dx. Now, what value of t returns us our original integral? Well, if t was equal to 1, you just have sine cubed of x left, which is what we originally had. So, therefore, this thing right here is equal to I of t is equal to 1. All right, let's go ahead and get into the meat. Let's go ahead and differentiate. I'm going to write it like this, d I of t over dt. Like we talked about earlier, we can go ahead and take the derivative to the inside of the integral. So the 1 over x cubed, you know what, it's fine. Let's go ahead and differentiate the entire thing with respect to t. Like that, okay. And so the x cubed is a constant, it's going to stay. So we still have the integral sign. Then we have our x cubed, it's going to stay. Let's differentiate the top first. So first of all, the entire thing is cubed. So we need to use power rule first. We take the 3 down, and then we take the sign, and then it is now to the n minus 1 power, 2, second power instead. To the inside of that, we have the trig function, sine. Differentiating sine, you get cosine. And then on the very inside of all of this, you have your argument of sine. Tx, well, the derivative of tx, and remember this is with respect to t is a variable, x is a constant, you just get x. Okay, bottom, you still have x cubed dx. This x and that x are going, and one of these x's actually are going to cancel out. So, yeah, in fact, let's move this 3 to the outside, because it's kind of nasty if we're going to leave it on the inside. On the bottom, you have x squared now. And on top, I want you to notice that we want everything in terms of cosine. Right, because if we have sine and cosine together, sure, sometimes it's going to work, but you can't do anything if there's still an x squared on the bottom. So instead what we're going to do is we're going to place the sine squared with a 1 minus cosine squared. And let's go ahead and distribute it in. 1 times cosine squared times normal cosine just gives you cosine. And then we had the minus cosine squared. Multiply that with the cosine, you get minus cosine cubed. And then on the bottom, you now have x squared instead of x cubed. You have your dx. All right. We had a trig function to the 3rd power earlier. Trig function to the 3rd power here. It's not going to do us that well, since if we just, I don't know, it's just, if we keep doing the 3rd power thing, you know, eventually it's not going to turn out very well. Instead, I'd rather have it be, you know, just the normal trig function with the different arguments. So, and where can we find a cosine cubed to replace? Well, yeah, which formula can we find a cosine cubed in? Well, we know that the cosine triple angle gives us a cosine cubed, right? But what is the triple angle? We're not completely sure. So let's go ahead and derive the cosine triple angle. All right. So we start off with cosine of 3 theta. Now this is equal to cosine of, you can break up 3 theta into 2 theta plus theta and then use the cosine angle sum. So the cosine angle sum is just cosine of the first times cosine of the second. You want to subtract off sine of the first times sine of the second. Alright, and then cosine of 2 theta right here, I'm pretty sure if you break it up into cosine squared minus sine squared is just 1 minus cosine squared. You get minus 1, and then minus cosine, positive cosine. Alright, cosine of 2 theta, I had to just think about this, is 2 cosine squared minus 1. You still have a cosine there, and then minus sine of 2 theta, I'm going to rewrite as 2 sine theta cosine theta. I left a gap there because, well, you have another sign that's being multiplied in, so it becomes sine squared. Alright, from here, go ahead and replace this with 1 minus cosine squared. Because once again, we want everything in terms of cosine. And you can go ahead and distribute this. So, you get cosine, 2 cosine cubed, and then minus cosine. Here, I'm going to do all the math, so mentally, right? 1 minus cosine squared. Just replace that with 1 minus cosine squared mentally. Distribute the minus 2 cosine into the 1 first. So you get minus 2 cosine, yeah? Because you're multiplying by 1. And then you have another minus cosine squared. Minus 2 times cosine squared minus times negative cosine squared. This negative and the negative that comes from the inside of the cosine squared, they cancel. You have a 2 left, so you have a positive, and you have a 2. This cosine and then the cosine squared, which gives you cosine cubed. So all in all, this gets you 2 plus 2 is 4. So 4 cosine cubed minus minus 1 minus 2 is just minus 3 cosine theta. Okay, and from here, remember what we were looking for. We were looking for an equivalent expression for cosine cubed. So we want to isolate this. How do we isolate it, right? It's not an equation. Yes, it is. This we can treat as the left-hand side. So this implies that cosine of 3 theta is equal to 4 cosine cubed theta minus 3 cosine theta. Let's go ahead and add 3 cosine on both sides. So you just have the 4 cosine cubed left on one side. On the other side, you added 3 cosine. So you have cosine 3 theta plus 3 cosine. Alright, and now all we need to do to get a cosine cubed by itself is divide by 4. So we get cosine cubed theta. We can replace it with 1 over 4 times cosine of 3 theta plus 3 over 4 times cosine of good old theta. Oh, alright. Let's go ahead and plug it in then for cosine cubed. Notice that we don't have theta here. Instead, theta, which is just supposed to be the argument, is tx. So we can go ahead and replace theta with tx and then put it all in here. So, I'm going to write this over here. We have the 3 on the outside, and then we have the integral from negative infinity to positive infinity. We have a cosine of tx. We're subtracting off. Cosine cubed is just equal to that guy right there. So, and remember our argument is now, our theta is just tx. So, in here we can put it 1/4 cosine of 3tx plus 3/4 cosine of tx. Oh god, almost out of room. And don't forget, it's all over your x squared buddy here annoying you, because without the x squared we'd be able to integrate and find that this is undefined, or it does not exist, right? Because these are technically limits. All right, from here what we can do is distribute out the negative, and then notice that this and that are like terms. And in fact, let's drag in the 3 again. So from there, I'm going to put down integral from negative infinity to infinity. Let's put down this right here, since there's only one of these. We distribute the negative and the 3. All right, so we get negative 3 over 4 cosine of 3tx. And then we get, distributing the negative again, you get negative 3 over 4, right? So distributing the negative, one of these guys minus 3 over 4 of these guys gives you 1 over 4 of these guys. So you get plus 1 over 4. Don't forget, though, you have to distribute into the 3. So this is actually plus 3 over 4 cosine. Did you not know I was recording? Could you not tell? Can you... Okay. When I'm recording, don't open the door because the camera's facing in this direction and the door is loud. Okay. I know. I heard you earlier. You're disrupting. You could probably hear it on the audio, okay? I got it. Okay, from here, this and that are like terms, so you can go ahead and distribute the negative and then deal with that. So, and in fact, I'm going to drag the 3 inside as well, so we can have the integral sign be on the outside. I'm going to put this down first, since there's only one of them. So we distribute in the negative, right, so you get negative, and distributing the 3, you get 3, and then it's 1 over 4, so 3 over 4, cosine of 3tx. All right, here, distributing the negative, one of these guys minus 3 over 4 of these guys gives you 1/4 of those guys. And then distributing the 3, of course, you get plus 3 over 4, and then just your cosine of tx. Right, so all over x squared dx. Okay, well, now what? We've got a cosine by itself and another cosine by itself. All right, phew. All right, okay. This is cosine, that's cosine. If we differentiated one more time, we'd be able to get a sine out of these two, right? So I think we should go ahead and try that. And along with that, that actually cancels out with one more x in the bottom. So you get sine of something over x, right? Plus sine of something over x. You get to use the Dirichlet integral that we found out earlier. Okay, so let's go ahead and differentiate this a second time, right? And it's not going to be all that bad. So, yeah, let's hit the second derivative. Right, this entire thing is equal to the first derivative. So I'm going to differentiate this, right? So this gives us the second derivative of I d squared of I of t over dt squared. This is equal to... Alright, once again, you can drag the differential inside of the integral sign, so due to the Leibniz rule of integration, that's how this works. Alright, differentiating this first term, differentiating negative cosine, you get positive sine. And then the argument stays the same. Chain rule says, since you're doing it with respect to t right now, the 3 and the x are constants. Bring them outside. And you're going to see the x from here and the x from here both cancel out the x squared. So I'm not going to put down an x for now. But so all we need to deal with this is 3. Bring the 3 outside. 3 times 3 over 4. 9 over 4. Right here, positive cosine. If you differentiate, you get negative sine. And 3 over 4 just stays. And then on the inside, you can also bring out of x, but once again, along with this x that you get from the chain rule here, it's going to cancel out with one of the x in the denominator, and in the denominator, you're just left with one more x. Okay, and we're almost there, because notice that, well, if you just split up the integral now, let's go ahead and try that. One integral, 9 over 4, on the outside, I'm going to take that to the outside, and then on the inside, you have sine of 3tx over x dx. Subtract off the 3 over 4 you can also bring outside. You're going to integrate with the same bounds. Sine of tx over x dx. Alright, and there you see it's almost in the same form. However, notice that inside of the argument of the sine, it's not exactly x. We want the variable to be the same, right? So, well, how do we do that? Let's go ahead and try to make some substitutions, and hopefully it's going to be the same. So, here, we're going to make the inside, let's just call it u maybe. Let 3tx equal to u. Oh, okay, first of all, we have the stray x just hanging out there, so let's isolate the x first. So dividing both sides by 3t, you get x is equal to u over 3t. All right, so that's first of all. Now let's go ahead and differentiate dx. Differentiating this side with respect to u, since u is our new variable, the u goes to hell, and then we have the 1 over 3t left, multiplying by not dt, du, since we are doing this with respect to u. That's also why the u disappeared. Here, let argument of sine is tx, and then this would be, let's choose another variable called w. You can't use the same variable, of course. Once again, you have an x hanging out here, so we want to isolate it. So x is equal to w over t. Dx is equal to, w is your variable dependent on x, so differentiating with respect to w, you get dw. 1 over t is just a constant, and then you have your dw. Ooh, alright. Let's rewrite all this. 9 over 4 stays on the outside. What about the bounds? Well, if you plug in a negative infinity into x here, negative infinity times whatever is still going to be negative infinity. Same idea with positive infinity, so the bounds are going to remain the same. Right, like that. Alright, and then we can go ahead and plug it in. So, sine of 3tx. 3tx is just u. And then on the bottom you have x. X is just u over 3t. Dx is 1 over 3t du. And you can immediately see that the fact that we made a substitution is not going to change the fact that we can use the Dirichlet integral, because right here the 3t and the 3t are going to cancel. Same idea that with the second integral right here. So this is minus 3 over 4. And, oh yeah, also same thing with the bounds, right? If you plug in a negative infinity into x here, the w is still going to be negative infinity. Same idea with positive infinity. It's going to be negative infinity to positive infinity. Sine of tx, well, tx is just w. So you get sine w over, and then x is w over t. And then your dx, right, is 1 over t dw. This t and that t cancel. So, at the very end of the day, you're left with 9 over 4 times the integral from negative infinity to infinity, the sine u over u du minus 3 over 4 times the integral from negative infinity to infinity, sine w over w dw. And I'm telling you this is the same as the Dirichlet integral because, well, once again, it doesn't matter what axis you're working on, it's still going to represent the same area. Okay, so earlier we saw this was pi, so go ahead and replace it with pi. 9 over 4 pi. Alright, and then here it's minus 3 over 4, and then also replace this guy with pi. 9 over 4 minus 3 over 4 is 6 over 4, which is 3 over 2. So this is 3 over 2 pi. Sorry, not 4. 3 over 2. And I'm going to put the pi in black. Okay, that looks like a final answer, but you have to notice that from here we get here, and then you get here, go here, here, here. And notice that this is actually the second derivative, right? So this isn't your final answer, and it's actually wrong, even if you took it to be. So now I have to go back into just into your primitive, right? The I of t by itself. So I'm going to go ahead and get rid of most of this. Of course, we have to put down the second we have to leave the second derivative information. That's pretty important. So we just get rid of everything else except for the information about which derivative. And then we can also get rid of all this cosine triple angle identity stuff. Okay, so I got rid of all the stuff that we're not going to be using. The second derivative is just that, right? So if we go ahead and where should I do this math? Yeah. So from all of this, I'm going to put it down here actually. So through all of this, we find that the second derivative of I of t with respect to t is just, well, it's equal to this, right, of course, but it's also equal to that. We reduced it. It's equal to 3 over 2 pi. Let's integrate both sides with respect to t. Integrating both sides with respect to, of course, this is squared because it's the second derivative, right? Integrating both sides with respect to t, you get the first derivative of I of t with respect to t. On the right-hand side, this is just a constant in the t world, so you have to multiply on a t. And don't forget you integrated, so you have to add c. And of course, we're going to integrate one more time, so there's going to be more than one constant. I'm going to call this c1. Okay, what is c1? Well, notice that I'm going to get rid of this now, thank God. Notice that the first derivative is not just equal to this, it's also equal to that, right? And in fact, let me just rewrite this out because I want this to be in the expanded form without the partial sign there. So integral from negative infinity to infinity of this would be 3 sine squared of tx cosine of tx, right, all over x squared dx. Almost done. All right, and then if you just, well, plug in a value for t, right, say t is equal to 0, this guy zeroes out, right, and we know that it's also equal to this, so you would plug in a 0 into t here. Sine squared of 0 is just 0, and that means it zeroes out the entire integrand, which zeroes out the entire thing. What you get is 0 is really equal to 0, so c1 is just 0, yeah? Okay, so you just get that. Let's integrate one more time. Integrating both sides, you get that I of t is equal to, well, integrate that one more time with respect to t, you get, you have to raise the power by 1, right, so you get t squared, and then divide by 2, so divide by the new power, so you can multiply on it 1/2, and that's going to give you 3 over 4 pi t squared, and then add your second constant, c2. Alright, and then I of t, of course, is just this. So to be able to find what c2 is, you just plug in 0 for t once again. Sine of 0 is 0, 0 over anything is 0, so, and integrating 0 gives you 0. So the left-hand side is just 0. It's right here. Plug in 0 here into t, you also get 0. So c2 is also equal to 0. Now remember that, okay, now we found what I of t is, so we're almost done. All we gotta do is plug it in. What value works for this to be equal to our original integral? Well, t is equal to 1. So we plug in I of t is equal to 1, right? First of all, we know that's going to give us our original integral. The integral from negative infinity to positive infinity of sine cubed over x cubed dx. But this is also equal to, well, we found an equivalent form right here. 3 over 4, and then you just plug in 3 over 4 pi, and then you plug in 1 for t. 1 squared is 1. 1 times anything is just the thing itself, so you just get 3 over 4 pi. That's it. You're done. That's this integral. Once again, using Leibniz rule for integration. Okay. Yeah. All right. Ooh. Oh, this pen's running out too. Leaving stains all over the whiteboard. It's okay, I think I can use it for maybe a couple more questions.